Welcome to this lecture on ordinary differential equations. Today we are diving into interacting population models. Imagine a pond with two species of fish competing for the same algae. How do we predict if one will survive or if both can coexist? By the end of this video, you will understand how to translate these complex biological relationships into elegant mathematical equations and how to solve them to predict the future of entire ecosystems. Let us get started. Now that we have introduced the idea, let us understand why we need these models. In the real world, species do not exist in isolation. They constantly interact by competing for resources, hunting each other, or even helping one another survive. A basic single species model only looks at the population's current size and the environment's carrying capacity. But that is not realistic for shared habitats. In an interacting population model, we use coupled differential equations. This means the rate of change for one population includes a mathematical term representing the presence of the second population. If they compete, this term is negative, slowing down growth. If they cooperate, it is positive. You simply cannot solve for one species without knowing the other. Before we look at two species interacting, let us review how a single species grows when it is completely alone. This formula represents logistic growth. Conceptually, a population grows quickly at first, but slows down as it runs out of food or space. Let us break down the symbols. The variable x is the population size. The symbol R1 is the intrinsic growth rate, which is how fast the population would grow if resources were infinite, measured in per time units. K1 is the carrying capacity, the maximum number of individuals the environment can support. As the population x increases and gets closer to K1, the fraction x over K1 approaches 1. This makes the term inside the parentheses approach 0, meaning the growth rate drops to 0 and the population stabilizes. This basic logistic formula we just saw leads us to an important question. What happens when a second species enters the exact same environment? If they compete for the exact same food, the presence of this new species will negatively impact the growth of our first species because there are fewer resources available. To represent this mathematically, we cannot just use the single species equation anymore. We must subtract a new term from our original equation that accounts for the encounters between the two species. Just like collisions on a highway depend on the number of cars in both lanes, the number of competitive encounters depends on how many individuals of both species are present. This new term will permanently link the two populations together. Now that we understand the concept of competition, let us look at the mathematical system that describes it. This is the Lotka-Volterra competition model. Conceptually, it takes two logistic growth equations and couples them by subtracting interaction terms. Let us look at the symbols. The variable y represents the population of the second species. The symbol alpha is the competition coefficient, measuring how much one individual of species Y hurts the growth of species X. Similarly, beta shows how much species X harms species Y. We multiply X and Y together because the interaction depends on both being present. If the population of Y increases, the negative term alpha times X times Y becomes larger, which physically means the growth rate of X decreases much faster due to heightened competition. Before we move on to solving these equations, let us visualize this relationship with a diagram. What you're looking at is a phase plane. The horizontal axis represents the number of individuals in the first species, X, while the vertical axis represents the second species, Y. Each curved line represents a different starting scenario for the two populations. Notice the arrows on the curves. These show how the populations change over time. Depending on their starting numbers and the strength of their competition, the populations shift until they converge at the black dot in the center. This point is the stable equilibrium, representing a perfect balance where both species coexist and neither population changes anymore. Now that we have seen the phase plane, Let us see this with a concrete numerical example. We are given a specific system of competing species and asked to find the equilibrium points. These are the specific population sizes where growth stops. To find them, we must set the derivatives, the growth rates, to 0. Why? Because if the rate of change is 0, the population size is frozen in place. We substitute 0 into the left side of both equations. This gives us a system of algebraic equations. For a product to be 0, one of the terms must be 0. So for the first species, either x is 0 or the expression inside the parentheses is 0. We apply the exact same logic to the second species to get our full set of conditions. Continuing with our conditions, we now find all combinations to locate every equilibrium point. The simplest combination is when both x and y are 0, giving us our first point at the origin. This represents total extinction. Next, we check what happens if species y is extinct, meaning y equals 0, but species x is not. We substitute y equals 0 into the condition for species x. Solving this simple equation gives x equals 2. This reveals the natural carrying capacity of the first species when it has the environment entirely to itself, giving us second point. We then do the reverse scenario. Assuming species X is extinct, we substitute X equals 0 into the condition for species Y. Solving for Y gives 1.5, our third equilibrium point. Finally, we look for the most interesting scenario, a point where both species coexist. This happens when neither x nor y is 0, meaning both parenthetical conditions must be true at the same time. We must solve this system of linear equations. We rewrite the first equation to isolate x, giving x equals 2 minus y. We then substitute this expression into the second equation. This standard algebraic substitution creates an equation with only one variable. Simplifying it gives 1 minus y equals 0, which means y equals 1. Substituting y equals 1 back into our isolated equation gives x equals 1. Our final answer is the coordinate pair 1, 1. Physically, this means if the environment has exactly one unit of each species, they will perfectly balance each other out forever. So, we have proven that coexistence is possible under competition. This brings us to a different scenario. What if the species actually help each other grow? Think of bees and flowers. This biological relationship is called mutualism, where both parties benefit from the interaction. Because they help each other, the mathematical structure of our model changes. Instead of subtracting the interaction terms because of harmful competition, the interaction terms in the differential equations will be positive. This positive term boosts the growth rate of both populations. Understanding this is crucial because it shows how cooperation can allow species to sustain higher population levels than they ever could on their own. Now that we understand mutualism conceptually, let us look at the mathematical system that defines it. Here is a specific system of mutualistic equations. Conceptually, this comes from the same logistic growth foundation, but notice the signs inside the parentheses. Instead of a minus sign for the interaction, we have a plus y in the first equation and a plus x in the second. Let us explain these terms. The plus y represents the positive boost that the second species provides to the first species. The plus x is the reciprocal benefit provided to the second species. If the population of y increases, the growth rate of x physically increases as well, because there are more beneficial interactions happening in the environment. Before we move on, let us see this mutualism model with a concrete example. We want to find the coexistence equilibrium point for this specific system. Just like in the previous example, we are given the equations and asked to find where the growth rates are 0. Since we are specifically looking for coexistence, neither x nor y can be 0. Therefore, the expressions inside the parentheses must be equal to 0 for both populations to stop growing. We set up our system of two linear equations based on this requirement. To solve them simultaneously, we take the first equation and isolate the variable y by moving the other terms to the opposite side. We then substitute this entire expression for y into the second equation. Continuing with our substitution, we now need to solve this equation. Why do we do this? Because having only one variable makes it possible to solve using basic algebra. We carefully distribute the -2 across the terms inside the parentheses, multiplying -2 by 2x and -2 by -4. This expands the equation to 5 minus 4x plus 8 plus x equals 0. Next, we combine the constant numbers, 5 and 8, to get 13. We also combine the x variables to get -3x. We move the 3x to the other side to make it positive, which is easier to work with. Finally, dividing both sides by 3 gives us the equilibrium population size for the first species as a precise fraction. Now that we have found the exact value of x, we must find the matching population for the second species. We substitute our fraction back into the isolated equation for y that we found earlier. We multiply the fraction by 2 to get 26 over 3. Then we convert the whole number 4 into a fraction with a denominator of 3, which is 12 over 3. We do this so both terms have a common denominator, required for subtraction. Subtracting the numerators gives us 14 over 3. This is our final answer. Physically, this positive interaction pushes their stable balance point higher up than their natural carrying capacities. They sustain higher population levels together than they ever could on their own. Now that we have used this formula and solved these systems, let us understand where this is actually used in the real world. Understanding interacting population models is absolutely critical across many fields. In ecology, park rangers use these exact differential equations to determine how many wolves they can safely introduce into a forest without accidentally driving the deer population to extinction. In medicine, epidemiologists treat a virus and white blood cells as two competing populations to understand immune responses. Even in economics, these equations model how two competing businesses share a limited customer base over time. Without these mathematical tools, managing wildlife, stopping a pandemic, or stabilizing an economy would be nothing more than blind guessing. We have covered a lot of ground today. So let us reinforce the most important ideas. First, interacting population models use systems of coupled differential equations to describe how species affect each other's growth. Second, by adding interaction terms to standard logistic growth equations, we can mathematically represent real-world relationships like competition or mutualism. Third, setting the growth rates to 0 allows us to find equilibrium points, which are the long-term stable population sizes. Ultimately, these models reveal whether species will coexist peacefully or drive each other to extinction. You have now mastered the foundation of interacting population models, giving you a powerful mathematical lens to view the natural world.